Good afternoon, ladies and gentlemen. Welcome to this pair distinguished lecture series. And you probably know that the pair conduct the distinguished lectures at least once a month. And today we are very lucky to have Professor Iain McCulloch from Princeton University to give a lecture entitled Designing Organic Semiconductors to Optimize Charge Transport. So it's really my great pleasure to introduce him. Professor McCulloch is a director of Adelina Center for Energy and the Environment and a professor of electrical and computer engineering at Princeton University. His research involves the design, synthesis, and the development of semiconducting small molecules and polymers. Those work significantly contributed to the development of organic semiconductors for applications such as organic thin film, transistors, photovoltaics, photodetectors, photocatalysts, and bioelectronics. A lot of applications, yes. So Professor McCulloch leads research at the intersection of energy, electronics, and biology, and has achieved great success in both research and technology transfer, bringing critical advances to the fields of optics, electronics, energy, and biological sensing, as well as scalable practical solutions to the biggest real-world environmental challenges. He has designed and developed carbon-based polymers that are central to innovative technology, to name a few. He developed new materials such as new electron acceptor materials, which boost the power conversion efficiency of the organic solar cells, and discovered new ways for harvesting solar energy, such as organic semiconducting nanoparticles brands that are efficient photocatalysts to produce hydrogen from water and the reduction of carbon dioxide. So it's a very long list, okay? I just try to skip a little bit, and I will say that he has a very extensive background in academia and the industry. You know, during the lunch, I just learned that he actually spent quite a lot of time in the industry before coming to the academia. But on the other hand, he has a very impressive citation history. Professor Wang Zhongkai, our Associate Vice President, just discovered that his citation is over 70,000 times, you know, within this very short period of academic career. And this is an enormous impact to our society. So I have to mention that Professor McCulloch is a fellow of the Royal Society. You know, this is very prestigious in the UK, and the Royal Society of Chemistry, the European Academy of Sciences, and a member of Academia Europaea. Among the many honors he received, he was awarded the 2020 Royal Society of Chemistry Interdisciplinary Prize. This is very relevant to pair, as well as the 2022 Royal Society Amorous and Braces Prize, which recognize excellent using user-inspired research on structure and functional materials that is both fundamental for the benefit of the society. So we are very much pleased that Professor McCulloch could come to Purdue to deliver this lecture in person. So without further ado, ladies and gentlemen, please join me welcome Professor McCulloch.
Wow, that was a very long introduction. I'm sorry about that. I didn't give you that. That must have taken yeah, you deserve a glass of water now and just to relax. So it's a great pleasure to be here. I can tell you right now, I have a much better view than you guys do. You maybe want to turn around and you can see it. It's really spectacular. So yeah, my name is Iain McCulloch. I'm currently Director of an Energy and the Environment Institute at Princeton University. I also have my research group at the University of Oxford in the UK, which is where I used to be before I went to Princeton. As was mentioned in the introduction, I am in the electrical and electrical and computing engineering department at Princeton. But as you'll see from my slides, I'm an organic chemist. I'm not an electrical engineer. But that's just the way that works at Princeton in terms of engineering departments. So I'm going to talk. This looks like a really boring title, right? Side chains and it's a very niche title, and I realized that typically for a university audience, it's quite a difficult job to try to bridge people who are maybe not interested in this, or maybe have got little experience in it, or are from a different field, or are just beginning their career as an undergraduate or PhD student. So I'm trying to pitch a sort of broad overview and then go into a little bit of scientific detail as I go along, but building from the first principle. So if it's boring to you about the first principles, I apologize, but hang in there. Maybe we'll get to something you like a little bit later on. So the work that I'm going to is mainly around the chemistry from my group here. Here are the people I work with. And a lot of the data that I'm going to show you is mainly around the characterization of materials through microscopy and electrical characterization, with a little bit of device application at the end. Not that new stuff, but some interesting stuff. Hopefully, you'll see from Shaika's group at KAUST. Okay, so just to start off, I thought I'd give you the helicopter view of organic electronics in the transport regime. And a lot of this data is actually dating from 2000, or maybe even earlier. And on the graph here on the bottom left-hand side of this slide, this axis that I'm showing you, the y-axis, is a parameter called charge carrier mobility. And this is the key parameter for material property, for the speed at which a transistor can work, the way that it can switch between on and off. And this is a very important parameter if you want to deliver high frequency or high current to a variety of different applications. You can think about maybe the traditional application, of course, for a transistor is an integrated circuit. But what we've been thinking about for organic electronics is not to compete with the highest performing silicon devices. So if you look at an integrated circuit in your computer, one of these chips from Intel, for example, they use 99.9999999% purity of silicon. The level of purification and processing that goes into these chips is just way beyond what we want to do with organics. We want to go after a different type of industrial technology. We want to go after additive processing. And the reason we're interested in additive processing is actually from an energy sustainability perspective. Modern photolithography techniques involving stepping, exposure, development, etching, repeat, uses and consumes a huge amount of energy. If we can move to a technology, if we can move to a technology that just involves stamping or printing, then it's a much more energy efficient technology. So we see a potential benefit, societal benefit in moving towards additive processing. But the applications we're looking at depend on the performance we can achieve with organic semiconductors. So this was the chart I'm mentioning here. So this is the historical context. And here we have the carrier mobility. And you can see that as polymers are developed through the ages here, the performance starts to creep up this axis. And what I've added here in red here is a threshold. This is the number 5 centimeters square per volt second. And this is assumed to be, or has been estimated to be, the threshold by which a technology becomes industrially manufacturable. So if we want to go after these high efficiency active matrix OLED displays, then we need to achieve this value. The first application, or what we call the entry application for organic transistors, is down here on the right-hand side. So I don't know how many of you might have, oops, I'm not sure if this is possible to use like a normal laser. I seem to be all over the place here. So this is a Kindle. This is an electrophoretic display application. It's a bistable display application. And what that means is that once an image is on the display, it stays on until it's actively removed. And that reduces the energy consumption considerably. So if you imagine a typical Kindle, you only have to charge it maybe once every 2-3 weeks compared to your laptop display, which consumes a lot of your energy. Also, the resolution requirements of these displays is very low. They're just printable resolution. They're not video rate. And that means that, again, the mobility requirements for the display underneath is much lower. The third part that makes this particular display attractive from organic electronics is that it's a reflective display. If you look at your laptop, that's an LCD, typically the transistor is embedded in a tiny component of the pixel. So it has to be small. And because it's small, it means the electrodes are small and it can't deliver a lot of current. The semiconducting performance, as a result, needs to be high to compensate for the small size of the device. Whereas in a reflective display, like a Kindle, the actual transistor can be the same size as the pixel. So it can be much larger. So again, the performance requirements are much lower. So you see here, the performance requirements for electrophoretic display is around 10 to the minus 2 centimeters square per volt. And that's achievable with today's materials. As we start to increase the complexity of the device and go to an active matrix OLED, and that's the things that I've been showing you here, then this 5 centimeters square per volt, 5 centimeters square per volt second threshold is pretty important. So just to give you an idea of how a display actually works, this is a cross-section of a display. We can see the transistor buried here. So this is what's called the gate electrode. This is a source and drain electrode. And a transistor is like a switch. So it goes from an on to an off state. And it does that through the application of a particular gate voltage when the source and drain voltage is on. So the current can either flow from the source to the drain, or when you apply a particular bias to the gate, it can switch it off. And the real beauty of a transistor compared to a resistor, for example, is that you're utilizing the semiconducting properties of the material, which means that they can, within 1 or 2 volts, you can switch the current by decades. So by 10 to the 4, 10 to the 5 amps difference, just by a 1 or 2 volts difference on the gate electrode. So this is one of the sort of beauty of a transistor. And if you look at an electrical circuit diagram of how this works, we have our circuitry, and this is our transistor. This is what a transistor looks like from an electrical engineering perspective. And this transistor switches the display effect on. And this can remain on due to the fact that in parallel to this, we have a storage capacitor. So our storage capacitor keeps our field across our display effect until we switch it off. So you need to have both the display effect, and this looks also like a capacitor, and we have our storage in order to be able to address this. So this is a very simplified picture of how a liquid crystal display transistor works. Thank you. And how an electrophoretic display works. When it comes to OLEDs, it's a very different circuitry. We now have what's called a gate transistor and a latch transistor, because we have to input a lot more current into the display. So an OLED, which you might have in your phone, is current driven, whereas an electrophoretic display and an LCD is field driven, it's voltage driven. So just to give you a sort of simple idea about how, from an organic chemistry perspective, I'm not sure if there's any chemists here, but to give you an idea of how we can use molecular design to tune the energy levels of semiconductors. So this is a key from a organic chemistry synthetic design perspective, is how we adjust the frontier molecular orbital energy levels. And we need to do this in order to be able to utilize all the features of a semiconductor, that is the charge transport, the charge injection, and the charge extraction. And so if we think about this as a simple molecule here I've drawn, this is a molecule we make actually as a solar cell material in our lab quite a while ago. And you can see here, you can model this by DFT modeling, just very simple density functional theory. And you can see we get an idea of the distribution of the energy levels, and we can calculate the exact energy of these energy levels as well. And this material, this molecule is characterized by having a very deep, highest occupied molecular orbital energy and quite a shallow, lowest unoccupied molecular orbital. So if you want to know what color it is, you need to think about the band gap. If you want to think about being able to take a charge and transfer it to another molecule, you have to be aware of these exact energy levels. So it's not just the gap between them, but it's the actual energy of the precise energy of these orbitals that matters. And so you can see here what we call the LUMO, a physicist might call the conduction band, and the valence band. And this has got a certain shape to it, because this is not each molecule has the exact same energy. They're in slightly different arrangements. And the broader this is, the more disorder there is in the molecule. So this is related to the density of states. So the energy between the two bands is called the band gap. And from a thin film perspective, the energy that it takes to inject an electron from vacuum energy into the conduction band is known as the electron affinity. And the energy it takes to remove an electron from the highest occupied level to vacuum is called the ionization potential. And so we need to know all the basics of how this works in order to be able to select the right molecules for the right application. And so when we go from this molecule here to this one here, if you can see this, what we've done is we've now introduced this thiophene unit. And what that does is that gives the molecule at rest more energy, more electron density. And when that happens, you can see we've gone from minus 5.82 now here, to a 5.55. So this has been a significant shallowing due to the energy density increase. At the same time, you see that the LUMO has actually dropped. And the reason that it's dropped is we've introduced electronegativity into the molecule, and that stabilizes the excited electrons that are in the conduction band. So by just substitution of very small amount of atoms in this molecule, we can significantly tune its energy levels. And this is the basis of what we do as organic chemists in order to be able to design molecules for organic electronics in general. So where does this come in a transistor? Well, for a transistor, we're not so much interested in the optics of the molecule. In other words, the band gap's not important. The energy that it absorbs with light or the energy that it emits is not the key. We're more interested in being able to inject charges from electrodes, because if you think about it, we have 3 electrodes in our transistor. We want to be able to take a charge and inject it into our semiconductor. It's then modulated by the gate and goes to the drain, as depicted here. So this is the cross section. And if we look at what's called a transfer characteristic, so this is the key electrical characteristic of a transistor. You can see that the current that flows between the source and the drain here as a function of the gate voltage has this type of shape. So if this was a resistor, it would just be a linear shape. But you can see that by changing the gate voltage here by only maybe 1 or 2 volts, our current increases by 1, 2, 3, 4, 5 decades. So 5 orders of magnitude. So that's why semiconductors are so expensive. They're not like a mix between a conductor and an insulator. They're something very unique. They have the properties of a conductor when they need to, and the properties of an insulator when they need to. They need to have the properties of an insulator when the device is off, and they need to have the properties of a conductor when the device is on. And if they don't have the properties of an insulator, the device just leaks and it's impossible to operate. And if they don't have the properties of a conductor, you can't get to the really high density, high resolution, very fast applications such as a huge OLED display. So they need to have both. And from a charge injection perspective, we're interested in if this is an electron device, if it's an N-type semiconductor, we're interested in the gap between the electrode work function and the semiconductor LUMO. We want to minimize that gap in order to be able to inject charge. This is an exothermic arrangement, a hetero arrangement here. The electrons will fall down in energy, so this is favorable. In this case, we also have a favorable arrangement for holes. So you want the electrode to be slightly deeper than the HOMO energy. If it's too deep, it becomes very leaky. So you want to be able to manage these. You see the work function of the 2 electrodes is very different as well. So if you want to operate an electron transport transistor, you typically use a lower work function metal such as aluminium. If you want to operate a hole transport transistor, you'll use a very inert metal, very large work function metal, gold or maybe even platinum to be able to access this HOMO energy level. Okay, so I'm going to now take a step into sort of historical times when the first organic semiconducting polymers were discovered and employed in transistors. And this is work from the Cambridge group quite a long time ago. And what they discovered was that the prevailing polymer at the time that was used is this polymer here called poly-3-hexylthiophene. So it has this conjugated thiophene backbone, and on each thiophene ring, there's an alkyl chain. And originally, the reason for the alkyl chains on that molecule was twofold. Firstly, it helped the solubility of the polymer to grow as you're synthesizing it. So in order for each chain, each repeat unit to be added sequentially along the polymer, it needed to remain in solution for the synthesis. So these alkyl chains helped that. The other reason is for the processing. If you want to use additive processing, such as inkjet or stamping, the polymer itself needs to be soluble. And what they neglected to think about was the role that these side chains have on the self-assembly of these polymers from solution. So it's just kind of taken for granted that these were inert components of the polymer. But in actual fact, we can see when Henning-Seringhouse's group looked at what's called the head-to-tail regioregularity. And what that means is that these polymers, this alkyl chain, has 2 choices of where to be to connect to the next thiophene ring. It can be, in this case, it's in the tail position with respect to this thiophene, or it could have been here in the head position. But when you have these asymmetric type repeat units, they introduce regioasymmetry, and that regioasymmetry can lead to disorder. And you see this in the case of this structure here. This is where we have a low regiosymmetry. Here, these alkyl chains are head to head with respect to each other, whereas these two alkyl chains are head to tail with respect to each other. And when you get this head-to-head coupling, you get these steric repulsions. And these steric repulsions change the thin film morphology. They change the crystallinity and they change the orientation of the backbone with respect to the thin film. And you can see this very nicely illustrated in the GWAX. This is grazing instance X-ray diffraction. And when we look at a polymer that has a very high degree of regional regularity, the backbone units are stacked edge on to the substrate. Whereas if we have a lower degree of regional regularity, the polymer chains, the backbone is now face on to the substrate. So this is a very dramatic change, right? Just by changing this side chain regularity, we could flip this orientation of our backbone from face on to edge on. And it's when we get the edge on orientation, we get this out of plane reflection in the lamella, this 1002,300. That's the de-spacing between, if you like the sandwich layers of this structure. So it's a very nicely lamellar structure. And when we have this, then the carrier mobility, this is this figure of merit I described earlier. This goes up now to about 10 to the minus 1 centimeter square per volt second, whereas this material that has a lower regional regularity has a much lower charge carrier mobility. So if we're trying to squeeze every little piece of performance out of our device, we want to go with the very high charge carrier mobility materials. That makes a big difference. So again, it's pointing towards the idea that these side chains are not as inert as we thought. So then my group looked at this polymer again, this P3HT. And then in this case, it's a perfectly regioregular P3HT. Each alkyl chain is head to tail to head to tail to head to tail, head to tail. So it's beautifully arranged, 100% regioregularity. However, when you look at the close packed distance between these chains, and you model this here on the right-hand side, so this was the work done by Joe Klein at NIST, what you can see here is, if we look at the angle at which our side chain projects from orthogonal, so this is the angle here, so this is 0, and then we start to increase this angle as we go to 90 degrees. You can see that the density increases as you start to tilt it. That's one thing. But what we also notice is that if you model this polymer and you interdigitate side chains, so in other words, if there's another P3HT just above and you bring it together, no matter what angle you can project this side chain from the main chain, at every single angle, you can see we've got a very high close packed density. Even at 0 angle, that's the minimum, right, when it's completely orthogonal. And that number of the close packed density in methylenes per centimeter squared is greater than polyethylene, than crystalline polyethylene. So that's not physically possible. Polyethylene has the perfect, or linear crystalline polyethylene has the highest possible packed density for an olefin, for an alkyl chain. So for this to be above that, it's not physically possible. So what that tells us is that P3HT, it's not possible for P3HT to interdigitate. So you have to think about these lamella as floating on top of each other. They don't actually come together. And when they don't do that, you can't get a three-dimensional crystal. You can only get one sort of lamella, like a sheet flapping in the wind. And if you're to press the sheets together to form a book, there would be no order in the vertical direction. And we thought about that, and we developed this polymer called PBTTT. And you can see it's very simple changes we've made here. We've just basically taken the poly-3-hexylthiophene, and we've introduced a thienothiophene, an unsubstituted thienothiophene group, to add a little bit of distance between these alkyl chains. You can see here these alkyl chains now are much further spaced apart. And very simply, that means now that vertically neighboring chains can come down and allow this interdigitation. And this is a process of self-assembly that encourages now a very nice degree of three-dimensional registration. So each layer is now registered to the layer above it, and we've got a large three-dimensional order. And we can see here that when we look at the close pack density, PBTTT here is in blue, we can see that there's an angle of side chain projection of around 45 degrees, where this number now matches perfectly polyethylene. And this actually is the tilt angle of the PBTTT side chain. So it projects that angle and it perfectly forms a very high density and very coherent side chain interdigitation. And why does that matter? Well, let's have a look at the thin film morphology. So here, this is P3HT. This is a 2G wax image. And you can see the reflection in the out of plane direction now kind of arcs a little bit. It's not spherical like in the bottom. Whoops, sorry. Down here. You can see here that the reflections, the intensity of this reflection is much more spherical and much tighter. So that means there's no off-axis misorientation. So these polymers are really beautifully ordered and beautifully oriented in a thin film. And we can see whereas the best P3HT thin film transistor carrier mobility, when you extract the mobility from these transfer characteristics here, the highest mobility we were typically achieving with P3HT was 0.1. But whereas when we take a very similar polymer backbone, but now introduce this side chain interdigitation to reduce energetic disorder, we're now able to get to carrier mobilities of an order of magnitude higher. So now much, much higher in performance. So we were quite pleased with that. So this was our PBTTT. We also did some STM imaging. And so this is a very high resolution STM. It's formed on a monolayer on a gold surface by electrospray. And here you can see, actually the best is probably to look up in the top corner here. The very light line here, that's the polymer backbone. And you can see the side chains here also beautifully interdigitated here. And this is this beautiful lamella. And if you actually just take a ruler and measure that distance between this backbone here and this backbone, and you measure that distance, it corresponds exactly to the X-ray. So this is a really good two-dimensional representation of the three-dimensional bulk. But you can see this long-range order of beautiful stitched. This is your 45-degree angle that I talked about earlier of the side chain to the main chain. And you can see this results in beautiful degrees of order. Whereas we made this other polymer down here, this is called IDTBT. And IDTBT, slightly high, slightly lower resolution. You can see there's not much, or what we thought at the time was, there's not much order here at all. You can't see really a lot of interdigitation. There is a little bit of short contact, but at the time we thought this isn't very good. And we thought what happens in IDTBT is the idea that we get this ribbon-like morphology. So the backbones are very coplanar, and there are reasons for that related to short contacts between, actually the biggest is a non-traditional hydrogen bond between the lone pair of electrons and nitrogen and this alpha hydrogen here. And we also get sulfur hydrogen interactions and sulfur nitrogen interactions. But all of these interactions between repeat units help to planarize the backbone. And these give rise to this ribbon. So even though it's a very wavy looking polymer, the actual backbone itself is very, very planar. Whereas the motif for PBTTT is of like sandwiches coming together. You've got this pi-pi stack, very strong pi-pi stack, and a lot of linear stacking. Transport is very fast within these lamella, but when you go to the boundaries, it's not always so good. Whereas in the case of IDTBT, there's these opportunities for very fast intramolecular transport and aided intermolecularly by these short contacts. I'll talk about this a little bit later. Here is our transistor, and you can see here now, in fact, IDTBT, which is a much lower order, less crystalline, we don't see evidence of the crystallinity, has actually got a much higher carrier mobility. So very nice characteristics. So this was a real puzzle, why something with much lower order should give a much higher degree, much higher charge transport. And we went back and we looked again at the side chains and the modeling. So this is our IDTBT here, our unit here. This is our benzothiadiazole, and this is our indacenodithiophene. And because this unit is not regiosymmetric, then depending on how these units orient along the backbone, they can have different conformations. So if we just look at this is one unit, one IDT, and this is a second unit. When we have the conformation where we have down, up, you can see that there's a spacing that's the same above and below the backbone. Whereas if we were to just twist this, and you can do that because these are just single bonds, if we were to just twist this orientation of one repeat unit, you can see now that there's a very different arrangement of the alkyl chains. So now the below the backbone is much smaller distance than above the backbone. So it's spread it out. So this gives rise to, again, to asymmetry. But the very interesting thing about PBTTT is it really doesn't matter in any degree of conformation you can think of for IDTBT. When you put two chains together above and below and you force the interdigitation, you can see that in each of these cases, there is a coherence of the side chains. So they can interdigitate nicely without any asymmetry or any lack of coherence at any point in the backbones. So we call this as a cis. So down, up is called cis arrangement. Up, down, up is called trans. And when you force an all trans conformation into another an all cis into an all cis, looks very nice. And no matter what you do, even mixed up, you just mix up the conformations and put them together with mixed or all trans mixed, it still works out such that you get very regular spacing between the side chains. And this is absolutely key, because when you look at IDTBT in a lot higher resolution, it's actually, we do see a lot of short length scale interdigitation. And so here's the backbone, and you can see the side chains here, hopefully. And you see this nice spacing here with the side chain density. So when you overlay this structure, you can see now that we have a very realistic representation of the backbone and also the side chains. It matches up, replicates perfectly. And you can see this happens when we put an all-cis conformation on the polymer. All right, I'm going to have to go through much faster. We then went and looked at this further by high-resolution TEM, and done by the Soleo group at Stanford. And in this case, they're taking a reconstruction. So this is not an image. This is a reconstruction of an image. And you can see that the lines are the polymer backbones. And one thing that came out of this was the crossing points. So there was a lot of crossing at almost 90-degree angle between the backbones. And there was very little parallel arrangement at short length scales. Almost all were the same angle. So we then went back to the STM and had a look at the STM. Remember, I told you that the way that electrospray technique, it forms a monolayer, but there are some instances where you have over crossing between two adjacent chains. And this backbone crossing was very consistent. And so we had a look at this. and you can see these crossing points. And we overlay the polymers so they fit perfectly on the STM. And you can see that this crossing only occurs at this space here. This is our benzothiadiazole unit. So what the side chains have done in this instance is they've pushed the crossing points to the part of the backbone where there is no side chain. So it's only at this point that we see this happening. So we'll again look at this a little bit further. So if you think about this polymer IDTBT, we published this first in 2010. And here, this is 14 years later, and there are publications still coming out looking at the modeling of how this polymer interdigitates and why the transport properties are so good. And what's come out of this work is that to maximize the charge transport in a semiconducting polymer, you really don't want to have parallel contacts, because the parallel contacts sterically block a lot of interactions. Whereas if you have perpendicular contacts, you have a lot, for the same length of chain, you have a lot more connection to other chains. And it's a combination of having a very planar low energetic disorder backbone and lots of contacts. That's the key message for being able to have high transport properties. So if the side chains push the contacts to the part of the backbone where there is no side chain, in other words, the BT part of this polymer, if we gave it more room, in other words, pushing the side chains further apart and introducing more free volume here, would that help facilitate these contacts, easier to find, and improve the transport properties? So we tried that, and in fact it did work. In this case, this is a TIFF BT. This is a slightly larger area for our short contacts. This is looking at the PDS spectra. You can see they're very low energetic disorder, but we've increased the carrier mobility by a factor of 2, just with this very simple change in being able to try to allow the backbones to assemble easier. Then we went, okay, let's go even further. So making these backbones even further apart. So we made this IDTBT, but this didn't work. The transport decreased. So we were a little disappointed because it was hard to make and a little surprised. And we went back to the model. I remember previously for IDTBT, there was no conformational arrangement where the side chains couldn't very nicely and very coherently interdigitate. But here you can see in the case of TBIDT, there's asymmetry in the spacing. And when you have that asymmetry in the spacing, you can't get rid of it by tilting, because it constrains on the free volume. And when you have that asymmetry, as you can see here, it gives rise to holes. So this is our TBIDT STM. This is the backbone here. And this is when we have this arrangement of all cis. You can see that there's a little hole here, slightly larger here. But when you have these large holes draw in ambient dopants, ambient contaminants, and these act to reduce the carrier mobility. They introduce disorder into the polymer. So that's not what we want to see. I'm going to, if I've got 5 minutes left, is that okay? 3 minutes? I'm going to talk a little bit about side chains, actually maybe more interesting for some of you in electrochemical transistor. So the difference between the transistors I've been talking about for displays and the transistors that we're now looking at here is that this is a bulk where the gate is now separated from the semiconductor, usually by an aqueous electrolyte. And in this case, we get mixed transport. So when we charge the polymer, then ions can come in from the electrolyte, you can see this here, and penetrate and compensate the charges that are injected into the polymer. So this is so-called mixed transport. Tends to be a little bit slower than for field effect transistors. But here the figure of merit, instead of just being the charge carrier mobility, is now the carrying mobility multiplied by this term called C star, and that's the volumetric capacitance. So it's not only important to think about the transport mobility, but also about the number of ions that you can pack into the polymer. And so to cut a long story short, we made a bunch of materials for this. This is an N-type material based on an NDI, naphthalene diamide backbone, and a bithiophene. But one of the key differences here is, in order to be able to accommodate ions, we need to have a hydrophilic side chain to be able to introduce aqueous channels for these ions to be able to come and compensate our charges. And so the big design criteria difference is now we've replaced these alkyl chains with glycol chains. So what does that mean? Well, glycol chains are not the same. They pack in a helical way. They're not as ordered, and they don't pack at as high a density. Whereas you can look at, if you look at PBTTT, this is an alkyl side chain, an all-trans alkyl side chain, very high density, the type of material you might get in a hip replacement, this high-strength polyethylene. Whereas the glycol chains, they wind around each other. And if you look at a single polymer with the glycol chains, you see the side chains here are curling up a little bit. There's not really any room now for interdigitation, just not as ordered. So this is the problem with OECT materials, is the lack of order due to glycolation. So we looked at a bunch of ways in which to minimize this, and one is to go from a ethylene glycol chain where there's one oxygen for every 2 carbons, one for every 3, and one for every 4. So we reduce the hydrophilicity, we reduce the swelling, and when you do this, your carrier mobilities increase. Your volumetric capacitance decreases, unfortunately, but you kind of win a little bit in the end. But this is the problem with the approach of reducing the ion content reduces your volumetric capacitance. So this approach worked a little bit, but we then explored other different approaches. Here we're introducing differences in the length of the side chains along the repeat unit in order to change the swelling by changing the interdigitation. So we have a very short chain and followed by a very long chain. This allows interdigitation, and when we get interdigitation, we get a very small amount of swelling. So relative swelling is small, and in this case, our carrier mobilities are large, but our volumetric capacitance is low. So again, you see that typically we trade off mobility and volumetric capacitance, and we reach a point where you get this sort of volcano type plot where you get this maximum somehow in the middle. But one interesting thing that came out of this work is that when you have a low degree of ordering and a low degree or a high degree of irregularity, low density, then when you start to repeat your transistor cycles, you see a big drop in the current. So the stability of these materials seems to be, to a large extent, inversely proportional to the water uptake. So we want to try to reduce that. Ways to balance this hydrophilicity also are by reintroducing alkyl side chains into polymers. When you do that, you can kind of have some alkyl-alkyl interactions, and these small amount of stitches along the backbone almost act as like physical crosslinks, and that helps reduce the swelling on water uptake. So that's also advantageous. I think I'll probably just stop here. I've got a couple more slides to show. Other ways we can reduce the swelling is by having not only alkyl chains on a sort of repeating units, but each chain could also have part alkyl and then part glycol. So you push the glycolation away from the backbone, and when you do that, you can introduce more order along in the backbone area, and that reduces the ability for ions to penetrate closer, which seems to help. Other things we can do is, again, looking at having the combination of interdigitation through the alkyl chains, as well as having these very stiff materials, which is a way again to help reduce this disorder. And all of these factors lead to an improvement in properties. But there's some work on other polymers where they don't have any glycol chains. BBL, for example, is a polymer where you have no glycol chains. And you say, well, I told you earlier you need glycol chains for solubility, for example, to be able to deposit these materials. This polymer can be fabricated in a thin film from acid, from concentrated acid. So it's not ideal. It's not, you know, for substrates as well. Some substrates don't work with this. But when you do that and you drive it off, you can see that you can get, in this case, a very high volumetric capacitance because there's no inert component. All the polar ions can be easily compensated by alkyl chains. So here we see that the mass uptake of our ions is much higher for BBL than it is from one of the polymers that I showed you earlier, forward and reverse. So these polymers have a much higher volumetric capacitance because it can be charged at higher density. So very new stuff. We haven't published any of this yet, but this is just one thing that we're doing now as well. Can we mimic this and get the best of both worlds? Can we get the alkyl chains for the solubility and then for the morphology self-assembly and then get rid of them? So what we've done here is we've introduced these thermally labile ester groups on the polymer backbone. And when we heat this, we can then remove them to form our acid. And when we do this, we introduce porosity into the polymer backbone. And this porosity allows aqueous channels to come in. So you can see if we look at this, the gas isotherm before and after the etching process, this is now indicative of a microporous polymer. And when we do this, we get higher currents and higher performance. And we're still working on this a little bit. And I think with that, finally, just to show an application, this is work done by CHEN Qingyan. You can see you can use these electrochemical transistors, in this case, to be able to sense for lactate. You can sense also for glucose. This is this paper here. Sorry, this one's glucose. This is lactate. And you see that when you add the metabolite to the enzyme, you add the lactate to the enzyme is reduced, and the reduced enzyme transfers electrons to our transistor, and you see there's a change in the current response. So when we're adding at the micromolar concentration, 10 micromoles of lactate, we see this jump and this corresponding jump in the source drain current. So we can use these as detectors for metabolites. And it's very versatile because the actual metabolite you want to detect, you just use a different enzyme. So in this case, this is lactate oxidase. It detects lactate. For this paper here, we use glucose oxidate. So you can change the enzyme, and each enzyme allows you to generate electrons, which can then be transferred. The problem is that the enzymes are pretty large, so the change in currents can be a little bit low. So I'll finish up there. I'm sorry about the technical difficulties that we had, and thank you very much for your attention.
So now it's open for questions.
Hello. Oh, thanks for the talk. I've got two questions on the talk actually. Well, the first one is, have you actually looked at the charge transport mechanism? I mean, you looked at obviously LUMO and HOMO, so that's, you know, to physicists that's covalence band, valence band, conduction band,
Yeah.
density of state. I mean, is that something that your chemists are not very interested, or
What do we look? What do you mean by?
like? So how does electron or hole transfer through this, you know, complex molecules?
So it forms a polar ion. So when you inject a charge into the semiconductor, it's a lower energy spread charge species. So it's a little bit like, imagine a bowling ball in a trampoline.
Hmm.
So at first you have your energy level, you throw the bowling ball in, it sinks down, and that sinking process determines the speed. So if you have a semiconductor where you've got low order or high disorder, the bowling ball sinks much deeper into the device. Whereas if you have a system that's well designed, coplanar, it's maybe like throwing a bowling ball in a marble floor. It bounces and it goes much faster. So if you think about that analogy, we can use that to design materials that have what we call non-covalent interactions along the backbone. And these non-covalent interactions create the superhighway, if you like. They reduce the amount of damping that's formed when you form a polaron.
Mm.
So this is what we call in chemistry the reorganizational energy.
Right.
Yeah. So, and you can think about this in terms of the Marcus theory. You could look at the extent of that, but having these systems where they have low reorganizational energy helps in that regard. But that's the theory. And in the end, it's really down to the short contacts, the number of short contacts that you have, and facilitating short contacts along a polymer, because it's the length scale of the device is much larger than the length scale of a backbone. So it's a necessity to have many interconnections between the electrodes. Even at the very highest resolution transistors, there's still hundreds of intermolecular interactions that are required in order to be able to bridge the gap. So we look at this in many different ways.
Right.
And the modeling's catching up now. It used to be that we would just add the modelling to a manuscript when it was finished. Now we actually look at it before we do the work at the beginning. And I think that's good evidence that, you know, that the theory is starting to help guide us in terms of our understanding of how to design these materials.
Right. So my second question is related to manufacturing. So how sensitive is your performance to polymerization or cross-linking? Or is that not a problem to
No, I mean, you've
scale?
already formed your polymer when you fabricate. So your polymer itself is already deposited. So the length of the polymer chain, maybe that's part of the question. So when you have a there's different conflicting views on this, but some of the latest work that's in the paper, I showed that Jenny Nelson's Proceedings of National Academy of Sciences paper. She shows that the mobility tends to have a monotonic relationship with length of chain, whereas in thiophene-like polymers, it's not like that. And the reason it's like that for these planar ribbon-like polymers is that the longer the chain, the larger the number of intermolecular contacts. The larger the number of intermolecular contacts, the faster transport you can achieve. So the length of it matters. The cross-linking only plays a role if you're worried about sequential deposition from solution, and if the solvent is going to dissolve the layer below. But most cases you can design that in such a way that that won't happen. You're going to use solvents that are outside the solubility parameter of the layer below. There's usually a solvent you can choose that doesn't have, because anytime you have post deposition chemistry, you typically lose in every aspect. You lose because there's local disorder that you're introducing due to a chemical reaction. And when something cross-links, the adhesion between layers decreases. The cohesion might increase in the layer, but because it's there's a slight densification, the layers lift up from each other a little bit, very small amount. That's what they use that for anti-adhesive properties. And so that's an issue as well. So if you can avoid cross-linking, you should do so.
Okay, so Any other questions? Oh yeah, please.
Professor, can I ask how your research can be applied for carbon neutrality or sustainability, because that's what my postgraduate degree studied.
Yeah. So obviously we're using carbon and we're using organic solvents. There are one or two things that we're trying to do. So if we think of it from a holistic perspective, any fabrication or manufacturing process that's less energy intensive is a benefit. So in general, fabrication by additive manufacturing has a much lower carbon footprint than conventional electronics, where there are many, many stepping layers, there are many development layers. It's not a full answer. We want to try to shift now also to water-based processes. So water-based processes from fabrication, for example, of nanoparticles that can coalesce on deposition. So a lot of our work, particularly in solar cells now, is moving towards water-based manufacturing. It also has its limitations, though, in terms of introducing water into a fab line where there might be low work functions, electrodes that might oxidize or might react. So there are challenges ahead. But this is, I think, a step towards reducing the carbon footprint of electronics where possible.
Thank you. Can I ask a bit of follow-up question?
Sure.
Besides green manufacturing of this semiconductor, can your research be used in other applications like novel PV units or something? Can you just elaborate a bit more?
Yeah.
Besides green manufacturing, I mean.
So in terms of applications?
Yes, that's what.
So one application completely separate to the talk today that we're working on a lot is photocatalysis of water to form hydrogen. So if you think about all these materials, if I just go back to very beginning. So think about electrochemistry. So in an electrochemical process, if you inject an electron into the LUMO, it sits here, it has a high energy. So it can undergo redox reactions, right? So either loss or gain of electron. In this case, it would be a loss of an electron. So it can drive a reduction reaction. And of course, the most common reduction reaction you can think of is a proton to hydrogen. So hydrogen evolution from water. So what we're trying to do is we're trying to inject, inject from an electrode would be electrochemical, but we're using photons in order to generate our electrons. And we do that by having a heterojunction structure where we take an exciton and then split it into a hole and an electron. When we have the electron in this LUMO, then we can undergo reduction reactions to form hydrogen. And at the other end, we're oxidizing water to oxygen. And these are ways in which we can think about solar fuels. We can think about valorization of CO2 through reduction to methanol, to methane, to carbon monoxide. So there are other reactions that we can do that are helping for example, decarbonizing fuels, storage, photovoltaic storage and things like that, energy storage. So these are things that we're thinking about.
Thank you very much.
Okay, so any other questions? Yeah, please. For a talk. Yeah.
Thank you very much for a very interesting talk. And I just wonder, the organic semiconductors are known to be affected by moisture and oxygen in air. And in this kind of approach to change configuration and also the packing of the polymer, can that problem be at least to be reduced or eliminated?
So I had a very good slide that would have shown that. I don't have that today, but there are many one electron reactions involving oxidation and reduction. And if you think about the redox chemistry, it's an equilibrium, right? So it's thermodynamics. It's a thermodynamic process, which means it's an equilibrium. And the problem with that from a stability perspective is essentially you can't have your cake and eat it. So if your semiconductor is ambiently stable in the neutral form, when you remove an electron, it's now reactive. So if you have good shelf stability, you have potentially poor inoperando stability. So there's the two go opposing each other. There are windows where you can take advantage of overpotential to help in that case. So you're using kinetics to fight thermodynamics. So in some cases you have, so for example, the reaction I've just shown here, that's very hard to avoid. It's quite hard to avoid the transfer of an electron from the LUMO of an organic semiconductor because there's many reactions. So if you think about a thermodynamically favorable reaction, if the half potential of your reaction is below the LUMO in energy, then it will happen. So you either have to deepen the LUMO to prevent these half reactions, or have to get rid of the materials that are involved in it. So if we just think about a reduction reaction, so what are the common reduction reactions? Well, of course, I just mentioned one would be taking an electron with water and forming hydrogen. Another is taking an electron with oxygen and forming a superoxide radical anion. That's a big problem because in combination with water, you form these peroxide or hydroxide radicals, and they chew all these structures up. So if you've got an electron transport material, you typically want to bring the energy level down as much as possible. In other words, increase the electron affinity. And what we see is that when we bring it down below the half potentials, you can add a little bit for our kinetic effect of overpotential. But when you bring them down, then they become operationally very stable. So I've been able to avoid these thermodynamic redox processes as an issue. With P-types, the original thiophenes were quite unstable because this HOMO energy level was quite high in energy. So it could be oxidized by oxygen. So you could take the electron away in the same way. But most semiconductors now have energy levels about 5.3, 5.4 electron volts. If it's very deep, then the actual polaron, so in operation, is very unstable. So it tends also, there are also traps all the way through of different energies in your semiconductor. So if you remove an electron from the HOMO, you've got your hole. The hole can fill all the traps above it. So the deeper the HOMO energy level, the more the trapping that can happen above it. So you want to try to push the energy level up this way to avoid all these traps. But when you do so, it's now susceptible to reduction. So again, that's a trade-off. These days, I think the common problems that they used to have with the stability of the thiophenes is no longer really an issue. And if you really look to long-term stability, look at an OLED. So an OLED has 3 organic species, red, green, and blue. And these materials are in the marketplace for 10 years now. If you buy an OLED television, you're going to want it to last 15 years minimum. So these are, in principle, if you make them pure, if you use kinetics, in other words, thinking about barriers, and then tweak the energy levels, you should be okay. So it's not as much a concern as it used to be.
Thank you very much for your kind sharing. It's very sharing the beautiful design of the organic semiconductor. I would like to ask a question about the size of the domain of this kind of material, because you design a lot of different structures, but we also know that this kind of the organic semiconductor material, they always have the gains boundary, then they would trap the charge there. How about in your design?
That's a very interesting. I don't have my laptop, but I would share other slides that I have on this. So we've looked at this quite a lot. So the worst kind of material, so there's also in a small molecule perspective, if you look at a herringbone motif versus a 2D slip stack, you can see very big differences in the effect of grain boundaries. A herringbone is much better for transporting from one boundary to another than a 2D slip stack, because potentially in a 2D strip stack, you've really orthogonal overlap. In polymers, poly-3-hexylthiophene does suffer from grain boundary effects. On the other hand, the most crystalline polymers here are maximum maybe 30% crystalline. The rest is pretty amorphous. I mean, that's the same with just about any polymer, unless it's monodisperse and it's really carefully processed. Generally, you have a lot of disorder, which means that the effect of grain boundaries in polymers is much less than in small molecules. Also, the domain sizes in polymers is much smaller than in small molecules. So a polymer domain size might be 10, 15, 20 nanometers. In a small molecule, it might be hundreds of microns. So you say, well, 100 microns is great because your channel length might be 40 or 50 microns, so that would be fantastic. But the anisotropy of transport for a small molecule means that it's a much bigger effect than in a polymer. So if you have the right orientation in a small molecule, it works really well, but it's very hard to be able to control the orientation of small molecules as they crystallize in a thin film. Actually, having polydomains across the structure evens out and reduces the anisotropy. You do have the grain boundary effect. And the way that we addressed that to some extent with polymers was the advent of, or the introduction of liquid crystallinity. So when you anneal a polymer, if you have a liquid crystalline phase in the polymer and you anneal above the melt, then in the liquid crystal phase, you can get quite nice sort of overlap between the grains. They tend to orient quite well with respect to each other. It's not such an abrupt interface. They tend to want to flow and have common orientation directions. So the effect of the grain boundaries, if you anneal a liquid crystal polymer within its mesophase, really reduces the effect of the grain boundary. But you're absolutely right. In a typical device that has, you know, if you want a very expensive transistor, you use a high resolution processing technique. If you're going after a much cheaper device, then you can use stamping or you can use screen printing or something to fabricate your electrodes, in which case you're talking about 100 microns, 200 microns or larger channel length. And so within that size, you're typically going to have hundreds of grain boundaries. So you have to pay attention to try to minimize that, especially for small molecule devices. And that's why small molecule transistors, they're not so popular now for these applications, because of the anisotropy and the grain boundary effects are too strong. The device. So if you've got, say, in a very simple integrated circuit, you might have 100 transistors. I mean, you've thousands and thousands in typical IT, but maybe in a simple display, you might have a ring oscillator that might have 10 transistors. For small molecules, the anisotropy means that the number of transistors that you can link is really low, whereas in a polymer, it's almost limitless. So if you want to build up a large integrated circuit, you can't use a small molecule for that reason.
Thank you.
Okay. Well, Professor Lee.
Hi, Ian. Very nice to meet you. To see you on campus. You showed a very beautiful STM, etc. Those electron microscopy pictures there. And of course, as we all know, that for soft material, that getting the atomic level resolution typically are quite challenging. So what's the magic there?
Yeah, I don't know if I can really answer that well because this is not my data. This is by Giovanni Constantini from Birmingham University. But yeah, you can, if you look here, you can see your beautiful backbone. You see the side chains. In fact, this is a 10 nanometer. I think I showed later on even larger. So now we're at 4 nanometers. So here, in fact, we might even go to 2 nanometers. Yeah. So here you really can see the carbons on the bridge here. I mean, it's not perfect. It's a little smudged. But, you know, we're at almost atomic length scale here. One of the potential limitations of this technique is that, you know, you do an electrospray on a gold surface. So this is a 2D, it's a monolayer. And there are people who say, well, how do you know that this image projects all the way into the bulk and it's not just a surface effect that's templated by the gold surface? But when in every sample we've looked at, if we see any type of order and we physically measure on the image the distance between polymer backbones and then compare that to the 3D bulk X-ray to look to see what that reflection corresponds to, they match perfectly. So I'm very confident that the type of assembly that you see on the surface of a gold is consistent with the 3D bulk. I think that's definitely the case. Is there magic here? I haven't seen many groups that are doing this, but I'm not sure if it's maybe this is a pioneering group that's been able to show this and other groups now are going to follow. There's nothing particularly, I mean, it's an STM and it's just electrospray deposition. I'm pretty sure it's possible for groups. I think maybe one or two other groups are doing it now. But I'm sure there's also a lot of know-how and a lot of expertise required. I don't think you could just walk up to an STM and repeat that.
Yeah, so it's wonderful. I have no doubt of the results. I just say that soft material is a kind of a electron beam damage. You can avoid that one and get it. That's amazing.
We see that more actually from TEM. So we have to do a lot of cryo TEM to avoid that. And we do a lot of, as well as low beam intensity as we can. But we still struggle with the TEM for, actually for nanoparticle, we're looking at heterojunctions. But that's a big, so when we move to the cryo, it tends to reduce the beam damage a little bit at least. But I'm not an expert in microscopy, so I can't really comment much more than that. Other than, yeah, I show some nice images, but I think that there's also probably a lot of tears involved as well, and a lot of times where it's not worked out so well.
Yeah, it's wonderful.
Well, yeah, maybe I take advantage as a chair to ask you the last question. So you demonstrate the excellent tunability of the swelling of your material, right? So you can change the swelling ratio from 1% to 200%.
Yeah.
Is there any trick to achieve this?
So the low swelling means hydrophobic, typically hydrophobic side chains. High swelling, less or more hydrophilic. So that's a very simplistic view. And then you think about, well, in terms of polar-on injection, how you can maybe have a backbone that has a very low reorganizational energy or very low disorder on injection, and that gets to quite a high level of packing. So if you can introduce interdigitation, that reduces the swelling, and we did that through short chain, long chain. The effects. Interdigitation is much harder in OECT materials, as I showed you, because of the glycol, the helical conformation of a glycol chain. It's harder to force interdigitation. So if you don't have the interdigitation, you get a much higher degree of swelling.
Okay.
When you introduce more aliphatic component,
Please,
then you reduce the
influence on
swelling.
the mobility or carrier transport for the material if we have a different level of swelling.
So I think that high degrees of swelling lead to disruption in percolation, increase in disorder, and reduced carrier mobility. I mean, I think there's a lot of like trade-offs, but so you need a certain level of hydration in order to facilitate the ions coming in, I think, a little at least. Although BBL,
Right.
but if you look into BBL, it has a lot of porosity in the way that it's fabricated, because it forms this. It's not a very soluble polymer. The poor fabrication actually works to its advantage because you generate a lot of micropores in there. That allows ionic channels, even though you've got no side chains. And I think that's the perfect model as a polymer without the propensity to swell, but the ability to uptake ions. And not easy, because if it doesn't swell, it's hard to dissolve it, to fabricate it. So alkylation close to the backbone is good, because then you can get ion penetration to a certain extent, but without disruption of the backbone. So
Right.
even if it swells a little bit, it doesn't seem to have the same consequential effect. That's basically what we're trying to do now, is to try to introduce aqueous channels outside of the electronic channels to separate them. At the moment, your ions just come right in and compensate the polar ions, increases the effective mass, increases disorder and disruption around the material. Now, what our design strategies that we're thinking about are ones where you have a charge transport channel and an ionic channel separate.
Right.
And I think
Okay.
that way you have hopefully no swelling, but still.
That could be a mixed ionic electronic conductor. Right?
Yeah,
So we have
but instead of the mixed nature interacting, in this case, it's slightly separated.
Okay.
So you don't have the negative consequences of ions. You need the ions also for volumetric capacitance, right? But if we can somehow bring the ions in but not have them slow down the charge transport, then that's, I think, a good feature.
Okay. Okay. Thank you. So probably we have time is almost time is up. So let's thank Professor McCulloch. Okay. Okay. Thank you.
Thank you, Professor Iain, for chairing the Q&A session. And of course, thank you to our speaker. I would just wish we have more time for the lecture and the Q&A. So to express our appreciation to your wonderful lecture, we make this special plaque for you.
Very much.